Hello, this is your review for Unit 3. So let me go ahead and go through the study guide problems for you. So this says find the derivative for all of this. And so we're going to need implicit differentiation because the x's and the y's are all mixed up. So every time you do a derivative of y, you have to chain on dy dx. So for ln of x, that derivative is just 1 over x. This would be minus 4y cubed dy dx. And then this would be 2e to the 3x, and then chain on derivative of 3x, which would be a 3. And so then you just need to get dy dx by itself. So I'm going to subtract this 1 over x to the other side. So like that's all the calculus. The rest of this is just going to be algebra. And then this would be 6e to the 3x. And I'm subtracting over that 1 over x. And then I'm going to divide everything by the negative 4y cubed. And basically, if it looks like a gigantic mess, then you probably did it right. Let me darken that up a little bit. There we go. All right, number 2, find the slope of the line tangent to that curve. So slope of the tangent line means derivative. So we're going to do the same thing like we just did in question 1, except then we're going to plug in 3 for x and 1 for y. So we're going to start out the exact same way. So this will be 4y cubed dy dx. And then this is going to be a product rule. And we have to subtract both parts of the product rule. We're subtracting the whole thing. So I know product rule is usually adding, but this time it's going to be subtracting. Or you think of it as distributing the negative sign into the product rule. But you have to subtract, both parts of it. So it's first times derivative of the second, that would be 3y squared dy dx. And then again, usually it's plus, but we're going to subtract the second times derivative of just x would be 1. All right, plus derivative of x squared would be 2x, and then derivative of 7 is 0. Do not try to rearrange this. There's no reason to. We're just going to plug in 3 for x and 1 for y. It's a lot easier to deal with numbers than variables. All right, so if y is 1, this is just going to be 4 dy dx minus, all right, let's see, y is 1 times 3 would be 3, and then times another 3 would be 9 dy dx minus 1 plus 6 equals 0. So 4 dy dx minus 9 dy dx, that would be negative 5 dy dx, this will be plus 5 equals 0. You would subtract over the 5, that would be negative 5, and then the negative 5s are going to cancel and you get 1. I wouldn't mark it wrong if you wrote dy dx equals 1, but technically it's dy dx at the point 3, 1. So technically it's, you should put in that such that bar and then at the point 3, 1. All right, number 3, write the equation of the tangent line to this graph at the point. All right, so to write an equation, you need a point and a slope. You have the whole point, so that's good. You just need to find the slope of the tangent line, which is derivative. So same thing like we just did in question 2. All right, so derivative, this is going to be a product rule, x times sine of y. So it's the first times derivative of the second. That'll be cosine of y dy dx plus the second times derivative of the first. All right, minus 2y, that would be minus 2 dy dx. Equals, that would be 10x to the 4th. Pi is just a number, so that derivative would be 0. Again, don't try to rearrange any of that. We just want to plug in 0 for x and pi over 2 for y. So if x is 0, this entire first part is going to just be gone, which is actually nice. Sine of pi over 2 would be 1 times 1 would be 1. Minus 2 dy dx equals, and then again, x is 0, so that would just be 0. So you would subtract over the 1, so that would be a negative 1, divided by negative 2 would be a half. So dy dx at this point is a half, and so that's our slope. So here's your point, here's your slope. We're just going to write the equation. Y minus pi over 2 equals a half times x minus 0. All right, number 4, same thing. We're going to write an equation at x equals 2. So this time we don't have the whole point. So we're going to have to plug in 2 for x and find y. So the first thing I'm going to need to do is get the point. So it'll be 2 something. And I'm just going to plug in 2 for x, and we'll see what we get. So 2 times 3 would be 6, minus ln of y equals, all right, 2 to the 4th would be 16. So I'm going to subtract over the 6, and then divide over the negative. And then to cancel out ln, you exponentiate. It's e to the power of, and we get y equals e to the power negative 10. Just that's some decimal. I don't know what it is without a calculator, but we're just going to leave it e to the negative 10th. Or if you want to be real particular, you can write it as 1 over e to the 10th. That's good. So that's our point. Now we need the slope that comes from the derivative. So here we go. Derivative of 3x would be 3 minus 1 over y dy dx equals 4x cubed. And we want to plug in 2 for x and e to the negative 10th for y. All right, so 3 minus 1 over e to the negative 10th dy dx equals, all right, 2 cubed is 8 times 4 would be 32. And then we're going to get dy dx by itself to get our slope. So subtract over the 3. Now this is 1 over e to the negative 10th. The negative exponent reciprocates that, so it actually just be e to the 10th. And then, gosh, what would that be? 29. So divide over the negative, it'll be negative 29, and then divide by e to the 10th. So negative 29 over e to the 10th is our slope. Again, that's some decimal without a calculator. I don't know exactly what it is, but it's just some number. And so this is our point. This is our slope. We're just going to put it together into the equation. All right, so I think that's the end of those. Yeah, now we're getting into the related rate questions. All right, so number 5, a baseball diamond is a square, 90 feet for each side. And those aren't going to change. No one is picking up the bases and running away with them. Although every time I do a problem like this, I always say it would be funny if we could play baseball like that. All right, but anyway, those aren't moving 90 feet on each side. That's constant. Batter is running from first base to second base. This is home. This is first, that's second. So he's somewhere in between here, running that way. This isn't to scale, but he's somewhere in between first base and second base, 25 feet per second. Find the rate at which the distance between the player and home plate is changing. So this is the triangle that we want to look at here. And this 90 feet is not changing, but he's running. And so both of these distances are changing. All right, so he is running at 25 feet per second. So our dx dt is 25 feet per second. We want to find the rate at which the distance between him and home plate is changing. So dy dt is our question mark. It should be positive because he's running away. This distance is going to be lengthening. And then we have to pause at a certain moment because, you know, he's moving, but we can only talk about one moment at a time. So it says when he's 30 feet from second base, that's not x. 30 feet from second base would be this distance. So if that's 30, that means x has got to be 60 feet. So that's all the information. We're going to set up a relationship between the variables. It'll be Pythagorean theorem, x squared plus 90 squared, that'd be 8100 equals y squared. Derivative 2x dx dt, 8100 is a constant, so that's gone, equals 2y dy dt. The 2's are going to cancel, and then we're going to look for everything to plug in. So x is 60, dx dt is 25. We don't have y, I'll come back for that, and dy dt is what we're looking for. So if you're missing something, you just need to do a side problem. I'm going to plug in the 60 for x. So 60 squared, that'll be 3600 plus 8100 equals y squared. And let's see, that would be 11,700 equals y squared. So square root of 11,700. Again, without a calculator, you just don't have to worry about it. It'll be 60 times 25 over square root 11,700 feet per second is dy dt. Non-calculator is better because you just don't have to worry about it. You can just leave your answer like that. All right, so next one. A searchlight is pivoting to follow a plane that is flying at an altitude of 3 miles. All right, so the altitude of the plane is not changing. It's at a constant altitude. So here's the plane flying this way. This is the light that's pivoting. So it's rotating like this. So that's the angle theta that we're looking at. And what was it, 3 miles in height. All right, the plane is flying 200 miles per hour. So I'm going to call that x. Dx dt is negative 200 miles per hour because as it's flying this way, that distance is getting smaller. So we're going to put a negative there. At what rate is the light pivoting? So d theta dt is our question mark. And that should be negative because again, as the plane flies over, that angle is going to be getting smaller. Again, you have to pause at a certain moment. It's when the plane is a horizontal distance of square root of 3 miles. So this distance is square root of 3 miles. All right, so we need a relationship between the variables. It's going to be tangent. Tangent of theta equals x over 3. It's opposite over adjacent. Then your derivative, secant squared of theta, d theta dt equals 1/3 dx dt. And then we're going to plug everything in. I'm going to come back to the secant squared. D theta dt is what we're looking for. And dx dt is negative 200. So if you're missing something, you just have to do a little side problem. I'm going to redraw the triangle for the one particular moment that we're talking about. This is 3. This is square root of 3. I'm going to do Pythagorean theorem to get that hypotenuse. So it would be 3 squared, which is 9, plus square root of 3 squared, which is 3, equals c squared. So that'd be 12. And so c is square root of 12. Let me just erase that. So secant is the reciprocal of cosine. Cosine would be adjacent over hypotenuse. Again, here's our angle. So cosine would be adjacent over hypotenuse. Secant is going to be hypotenuse over adjacent. So square root of 12 over 3. And so we're going to need to square that. That would be squared and square root cancel. That'd be 12. 3 squared is 9. D theta dt, this is negative 200 thirds. 12 ninths, would that reduce to 4 thirds? And so to get d theta dt by itself, we would multiply by 3/4. We're going to multiply that over. So the 3's are actually going to cancel. Negative 200 divided by 4 would be negative 50. The units are a little tricky for this one because it doesn't actually say it anywhere in the problem, but theta is always in radians. So that's going to be radians per the time was hours. That was miles per hour. So our time was in hours. So negative 50 radians per hour. All right, number 7, this is the tank that's filling up. I'm going to give you the formula for volume of a cone. So the tank is being filled up at 7 feet cubed per minute. You can use that as a clue that that's about volume. Since it's cubed, it's 3-dimensional. It's filling up, so that's positive 7 cubic feet per minute. The cone has a radius that is 1/4 the height. We want to find the rate of change of the depth of the water. So that's dH dt. It should be positive because it's filling up. When the depth is 4 feet. So when the height is 4 feet. And here's our volume. Volume is 1/3 pi r squared h. We have to get rid of the radius because I don't have any information about the radius. I only have information about height. I'm looking for something about height, the rate of change of the height, and I have the height at a particular moment, but I don't have the radius. So we're going to plug in this 1/4 h for r. And so you just have to get through these few steps of algebra. Now I'm going to square that. So a 4th squared would be 16, h squared is h squared. A 1/3 times the 16th would be a 48th. So 1/48 pi h cubed. You have h squared times h, so h cubed. This is all algebra. And you just have to get through that substitution and working that out. Now we're going to do the derivative. So dv dt equals, multiply the 3 down. You can leave it as 3/48, but that would reduce to 1/16 pi h squared dh dt, and then plug everything in. dv dt is 7. H is 4. Now this one kind of turned out nice because 4 squared is 16. So the 1/16 and the 16 kind of cancel. But if that didn't happen, you can just divide all of this over. Again, you don't have to simplify it down. But in this case, since that canceled, all I have to divide over is the pi. So 7 over pi feet per minute. It's just feet per minute because it is just the rate of change of a height. A height is one dimensional. This was cubed because it was rate of change for volume, but we just found rate of change for height, so just feet per minute. All right, number 8, this is the ladder problem. 15-foot ladder is sliding down a wall. So here's our 15 feet for the ladder. I'm going to call this X and Y. The bottom is being like pulled or pushed out and the top is sliding down. The foot of the ladder moves out at a rate of 2 feet per second. So that is dx dt. How fast is the top of the ladder moving down? So that's dy dt. It should be negative because it's sliding down. When the foot of the ladder is 9 feet from the wall. So when x is 9. So Pythagorean theorem. And then your derivative. Derivative of a constant will be 0. If you go through and divide by 2, all the 2's are going to cancel. 0 divided by anything would still be 0. You can leave them in there, but I'm just trying to make the numbers smaller for us. All right, x is 9, dx dt is 2, y we don't have, and dy dt is what we're looking for. So I'm going to do a little side problem, plug in 9. Actually, I think this is going to be a 3, 4, 5 triangle that's scaled. I think that's what I made it. This is 9, this is what we're looking for, this is 15. If you notice that you can do Pythagorean theorem, but if you notice this is 3 times 3, and this is 5 times 3, so y is going to be 4 times 3. It's a 3, 4, 5 triangle that got scaled. So y is going to be 12. But if you notice that, great. If not, you can do Pythagorean theorem, you'll still get 12. So this would be 18. We're going to subtract that over. So it'll be negative 18, divide over the 12. That reduces, but you don't need to worry about it. Feet per second for your units. All right, number 9, we are going to need a calculator for this one. We are cutting squares of equal size off the corner of a box, or sorry, the corners of a piece of cardboard. We're going to create a box out of it. So here's our piece of cardboard, and we're going to cut out squares from each corner and fold up the sides to create a box. So we're looking for the volume here. So it was 10 by 14. This is very much not to scale. So if we're going to do length times width times height, the length was 14, but we cut a square out of each side. So 14 minus 2x. And then the other dimension would be 10 minus 2x. And if you fold these up, the height is that length x. So we're going to have a little bit of algebra to work out here, multiplying this all together. So 14 times 10 would be 140. This would be minus 28x and then minus 20x. So minus 48x plus 4x squared. And then I'm going to distribute that x through there. All right, and then we can do the derivative. So 140 minus, gosh, what is that? 96x plus 12x squared. And we are looking for the largest possible volume. So I am going to need my calculator at this point, and I'm going to need to pause here because I didn't grab a calculator. Let me go get one. And I'm sorry, I just realized I wrote dv dt. This is an optimization problem, not a related rate. Nothing is moving. Sorry, I'm just going to call this v prime. The box is not running around. It's not a mobile box. We're just looking for the largest possible volume. So I want a critical point here. We're going to set this equal to 0. Sorry, we just got done doing all those related rate problems, and my brain was like dv dt. All right, so what we're going to do is go to y equals and plug in this derivative. So 140 minus 96x plus 12x squared. And it's going to be a parabola, so we'll get 2 critical points. The one you want is this one. We're looking for a maximum. So you want to change from positive to negative. It looks like it's right at 2, but it's probably not perfectly 2. It's probably like a little bit of a decimal there. So we're going to do calculate 0. Left bound, I'm going to do 1 enter. Right bound, I'm going to do 3 enter. Guess, I'm going to do 2 enter. And it comes up 1.918. All right, so we want x to be 1.918 inches. So that's what this distance would be. And then to get the volume, you're going to plug that 1.918 back into the original equation. And what's cool is right now the calculator has x stored as that. So if you go back to the home screen, you can just type 14 minus 2x times 10 minus 2x times x. Like you can just type that exactly and it'll plug it in for you, which is really cool. So 120.164 inches cubed because it's a volume. So you need that to be three-dimensional. All right, number 10, another optimization problem. We are fencing in an area using a barn as one side, which is good because then you only have to create three sides of the fence. I'm going to call it X and Y. We are looking for the biggest possible area. So area is length times width, that's X, Y. The problem is that's two variables, so I've got to substitute one of them out. Let me see, how much fencing was there? 300 feet of fencing. So if you add these up, X plus 2Y should be 300. I'm going to subtract over the 2Y, and that gets substituted in for X. And then I'm going to distribute the Y through there. And then we're going to do the same thing with the box problem that we just did. It's going to be derivative equals 0, because if you want a maximum or minimum, that's a critical point. So this derivative would be 300 minus 4y, set it equal to 0. You would add over the 4y, 4y equals 300, and then divide by 4. So that's going to be 75. Was this feet or yards? What did I make this? Feet. So y is 75 feet. We need to find x. So if this is 75 and this is 75, that's 150. And it was a total of 300 feet. So x is going to have to be 150 feet. And then for your area, you're just going to multiply those together. So, and I'm just typing this in the calculator. I'm not doing that in my head. 11,250 square feet area is two-dimensional. All right, do the following functions satisfy the hypotheses for Rolle's theorem on -2 to 5? So it needs to be continuous, differentiable, and start and end at the same place. This one's going to be a no. It is not differentiable at x equals 4 due to the sharp edge. This didn't ask for a reason why, it just said yes or no. I'm just putting that to be like extra thorough. This is a quadratic and this is a cubic. So those are continuous and differentiable. We just need to make sure they start and end at the same place. And it doesn't matter what these come out to, they just need to be the same thing. So if we plug in -2, that's going to be 4 plus 6 minus 10, that'll be 0. If we plug in 5, we get 25 minus 15 minus 10, which is also 0. So this one's a yes. Sorry, I ran out of room there. This one was no, this one is yes. And here, if we plug in -2, that'll be -8 doubled will be -16 plus 10, so -6. And if we plug in 5, I'm not going to work this out any further. If you do 5 cubed, 5 times 5 times 5 is 125. I know that this is not going to come out to -6. Whatever it is, I know it's not -6. So that one's going to be a no. All right, number 12, does this function have a value c on this interval such that f of c equals 0 justify? This is intermediate value theorem. This function is continuous because it's a parabola. We just need to show that 0 is in between the other two outputs. So we're going to plug in -2 and we're going to plug in 3, and we just need to show that 0 is in between. So if you plug in -2, that'll be 4 plus 10, so 14. 3 would be 9 minus 15, so -6. So 0 is in between them. So we're going to say yes. Since f of x is continuous on -2 to 3, and you can be as wordy as you like here, but the most succinct way to put it is that 0 is in between these. So f of 3 is smaller than 0 is smaller than f of -2. So since all that is true, then you can just repeat the question. There is a value c on the interval, blah, blah, blah. You can just repeat the question. There is a value c on -2 to 3 such that f of c equals 0. And here we did it for 0, but you could do it for any number. So like say it was f of c equals 3. 3 is in between these, so you could use it to justify that as well. All right, 13, let f of x be a polynomial such that f of 3 equals -1, all right? That just means you have the point 3, -1. Derivative equals 0, that means it's a critical point. And the second derivative is -4. It doesn't matter that it's -4, really just that it's negative is what is important. If the second derivative is negative, your graph is concave down, and that means that that critical point is a relative maximum. So that's your second derivative test. All right, find the absolute maximum and minimum of this function on the interval. I am going to need a separate piece of paper for this one. All right, absolute maximum minimum is your candidates test. You're going to start out by finding your critical points. So this derivative, you're going to bring down the 3, it's going to drop to a 2. All that stuff inside is going to stay the same. And we're going to chain on the derivative of the inside part, which would be 4x plus 4. Set it equal to 0 to get the critical points. Now, if you divide over a 3, 0 divided by 3 would be 0. And you're going to set each of these factors separately equal to 0. For this one, square root to get rid of the squared, but square root of 0 is 0. 0 is nice like that because it gets rid of all that stuff. So just looking at this factor, we can take out a 2x, be left with x plus 2. And so that gives us 0 and -2. And then if you set this one equal to 0, you're going to get -1. Now your candidates are your end points and your critical points. So here's our end points, -3 and 2, and then all of our critical points. So -2, -1, 0. And we're going to plug those into the original function, which is right here. So -3 squared, that'd be 9, double that is 18, minus 12 cubed. So what is that? 6 cubed, which would be 216. If you didn't happen to know that off the top of your head, you could just write 6 cubed. That's fine. All right, -2 squared before, double that is 8, minus 8 cubed. All right, so that's just going to be 0. For -1, we'll have 2 minus 4 cubed. That'll be -8. If you plug in 0 for these x's, you're just going to get 0. And then 2. 2 squared is 4, double that is 8. Plus 2 times 4 is 8 cubed. So that's 16 cubed. I don't know what that is off the top of my head, but I know that that's the biggest number out of all of our results. So our absolute maximum is 16 cubed at x equals 2. And our absolute minimum is, what was the smallest one? -8 at x equals -1. That is your candidates test, your endpoints and your critical points. Plug them into the original function, just see which one's the biggest and which one's the smallest. All right, number 15. Here's our function on this interval. Does this satisfy hypotheses for mean value theorem? Just has to be continuous and differentiable, which it is. So yes, if you circled yes, which we did, find the value guaranteed by the theorem. If we said no, justify why not. All right, mean value theorem. Mean means average. So your average rate of change equals your instantaneous rate of change. So to get your average rate of change, you need a slope. So we're going to get our 2 points. We're going to plug in -4 and -2. All right, -4 cubed, that would be -64 and then plus 8. So gosh, was that -56? Yes, all right. And then plugging in -2 cubed, that would be -8 and then plus 4, so -4. So if we do the slope, it would be -4 plus 56 over -2 plus, gosh, everything was negative there. All right, so it's going to be 52 over 2, which will be 26. All right, so our average rate of change is 26. We're going to set that equal to the derivative, which the derivative would be 3x squared minus 2. So we set our average rate of change equal to our instantaneous rate of change, and we're just going to solve that. So add 2, you would get 28. Divide by 3, 28 thirds. Square root. Now, when you square root, you put plus and minus. We only want the negative result this time because the negative one is the one that would be on that interval. So that is our answer. All right, number 16, we're going to go through this entire process. So first, letter A, find the critical points. So that is derivative equals 0. All right, so this derivative would be 2x cubed minus 8x squared plus 8x, set it equal to 0. We can factor out a 2x. And then this is going to factor into x minus 2 squared. So our critical points are 0 and 2. Letter B, intervals of increasing and decreasing. I'm going to make number lines for each of these. This one's positive all the time because it's squared. This one's going to change at 0. It'll be negative and then turn positive. So we have decreasing and then increasing. Your sentence should start f of x is or f of x has, because that's the function you're talking about. So f of x is increasing 0 to infinity because derivative is positive there. F of x is decreasing negative infinity to 0 because derivative is negative there. All right, C, for each critical point, so for 0 and 2, you have to write 2 sentences here. State whether we have a relative maximum, minimum, or neither. So at 0, derivative changes from negative to positive. So f of x has a relative minimum at x equals 0 because derivative changes from negative to positive there. And at, what was it, 2, we have no change. 2 would be over here. You could say f prime does not change sign there, or you could say f prime stays positive there. I usually just say does not change sign, because it could be stays negative and you don't want to get it wrong. All right, f of x has neither a relative maximum or minimum at x equals 2 because derivative does not change sign there. All right, part D, I'm gonna need a new piece of paper. Part D, find the x values of the inflection points. All right, let me copy from the paper that I just had. Our first derivative was 2x cubed minus 8x squared plus 8x. So we're gonna get the second derivative, which will be 6x squared minus 16x plus 8. We can divide everything by 2, which is nice because 0 divided by anything is 0. And then we're going to factor this. So that will split 3x and x. 4, I think we want this to be 2 and 2. Let's see. Yeah, we would want -6, -2 will give us -8. And so we get 2/3 and we get 2. And then part E, this last part here, is state the intervals for concave up and concave down. So I'm going to make number lines for each of these. This one has a change at 2/3 from negative to positive. This one has a change at 2 from negative to positive. And so we have positive, negative, positive. So f of x is concave up negative infinity to -2/3 and 2 to infinity because second derivative is positive there. And then f of x is concave down -2/3 to 2 because second derivative is negative there. All right, and then here is the last one. We have a function that's continuous from -1 to 4, twice differentiable, except for these values where you have does not exist. Critical points, that is where the first derivative equals 0. So we're looking at this row. We want where the first or 0 or undefined, I'm sorry, 0 or undefined. So we have a critical point at -1. Let's see, also 0 and 2. So -1, 0, and 2 for our critical points. It's where your derivative is 0 or undefined. Points of inflection. Now that is where your second derivative changes from negative to positive or positive to negative. There has to be a change. Critical points are critical points no matter what, but inflection points, there has to be a change. So here we have the second derivative is undefined, but we don't get a change in the sign. It's negative and it stays negative. So that doesn't count. So here we have one, we have a change from negative to positive. So at x equals 1, and that might be it. Yeah, then we're positive for the second derivative from then on. So the inflection points are a little bit more picky. And then we're going to graph this. So these are the points that you're going to plot. So -2, 3, -1, 0, 0, 2. I kind of like this. This is just like playing connect the dots here. Now you don't need to worry about the first derivative. That tells you increasing and decreasing, but it's just going to happen. Like you can't get from here to here without decreasing, or from here to here without increasing. So like that's just going to happen. You really just need to look at the second derivative for the concavity. We want to be concave down, so just make this bend downwards, and then still concave down all the way until 1. So we end up with a cusp there, and that's why these derivatives does not exist, because you have that sharp edge. And then at 1, we have a change to concave up. So we're going to be concave up from 1 to 3.